Well, thank you, and thank you for having me back. I had a wonderful time last year when I came up here, and it's great to be back again. The weather actually is wonderful, isn't it? Yeah. Who would have thought that in early November in Chicago area you'd be eating outside, no jackets, I had air conditioning on in the car yesterday. I didn't think that was ever going to happen. It was amazing. I got news for you, that ain't going to last. You won't see this again until probably May. So things are a little warmer where I live, but this is the last hurrah, I'm sure. So the last waning days of autumn. Well, I'm going to talk about some dark subjects tonight, the black holes, dark matter, and dark energy. And the reason why I talk about this and like to talk about this is the fact that I found that many creationists are very suspicious of all of these things. And I'm not so suspicious, particularly the first two I'm very bullish, and the third one is actually good evidence for, but we may want to reinterpret that a different way. I'm going to spend most of my time on black holes, and then I'm going to spend much of the remaining time on dark matter, and then I'll finish up with just a little bit at the end with dark energy. Now, the question many creationists have is, do these things exist? After all, we don't see them. And so the reasoning is, well, seeing is believing, correct? And if these things don't give off any light, how could you see these things? And then the other objection is that aren't they just hypothesized to salvage evolutionary theories? Aren't they like rescuing devices that have been created to make the Big Bang work, or star formation work, or galactic structure work, and these sorts of things? And so again, the three things are black holes, dark matter, dark energy. Again, they kind of go together well with that motif of things that go bump in the dark. All right, well, do they exist? Can we see them? Well, I would submit to you that there are many things that you probably believe in that you've never seen. Like, for instance, you probably believe electrons exist, but you've never seen one. And it's not just you. No one's ever seen an electron. But there's a tremendous amount of indirect evidence that tells us electrons are real. Have you ever seen air? Well, it's never good when you can, right? But hopefully the air is clear, but yet hopefully you believe in air, don't you? And you can't see wind either. Sometimes my wife you'll like this, Ken, look out the window. Look at the wind, she says. And I said, that's nonsense. You can't see the wind. The trees are going like this, and technically what you're seeing is the effect of the wind. So there are many, many things, physical things that we believe in, yet we don't see them, and we still believe in them. So saying you can't see something isn't really good enough reason not to believe something. And many times these things, the evidence is indirect. I mean, have you ever seen your brain? No, it's not a good thing when you see your brain either. But yet I hope every one of us has one tonight. And there's good evidence that such things exist. I go on and on with all sorts of examples of things we've not seen before. And are they evolutionary? Well, as it turns out, there are many, many things out there that creationists look at and the evolutionists talk about, and the evolutionists interpret them in terms of their evolutionary theories. We don't go around denying that these things exist. Like, for instance, antibiotic resistance. Evolutionists like to talk about that. They say that's evolution occurring right before our very eyes. But yet we creationists have an explanation for that. I think a better one for that. What about Grand Canyon? How many times have you heard about millions of years with Grand Canyon? But nobody ever says, no creationist says, well, the Grand Canyon doesn't exist. To the contrary, we say, no, the Grand Canyon does exist, but it didn't take millions of years, and we have a better explanation, we think. So why can't we, when we come to black holes, dark energy, dark matter, maybe there's a good creationary explanation right there. Why are we throwing it out without going through it very carefully? It's very important, I think, that we separate the physical data to support these things from the speculation about these things. And I would think, of all people, creationists would be very sensitive to this, because we do make a distinction between two types of science. We have operational science, sometimes called experimental observational science, and then we have historical or origin science, where we start talking about where things came from. One is about the science of the world as it exists now, the here and now, and the other one is the study of trying to figure out where things came from. And so it's very important when we look at these topics that we don't concentrate on all the evolutionary musings, just look on the data for these things together. Well, let's talk about talking about talking about matter, things that are there. And I want to talk right off the bat about mass. How do we measure mass? What is mass, by the way? Anybody know? Mass is a measurement of how much matter you have. Now, if you think, I can use a more technical term if you wish, it's how much stuff you have, all right? You like that? I like the word stuff, all right? So matter is stuff. When it comes down to it, in physics, we use a lot of things. We know a lot about certain things. We don't know what they are. Like, for instance, matter. I don't think anybody knows what matter is, but we know a lot about it. We don't know what time is, but we know a lot about that. And we don't know what space is, but we know a lot about space. And we don't know what a lot of things are, but yet we understand a lot about it. It's really kind of weird when you think about it, the philosophy of these things. But I digress. Okay, how do you measure your mass? How much matter you have? How do you measure that, folks? You ever do that? A lot of you probably did it already today. Maybe do it every day. What do? You step on some scales, right? And you get upset, right? Because you don't like what you're reading. You're going to throw the scales out because they're lousy. Now, what you're checking there is not your mass. You're checking your weight. Weight and mass and matter are related, but they're not the same thing. Weight is the force of gravity between you and the earth, and it depends upon several things. It depends upon your mass, it depends upon the mass of the earth, it depends on the size of the earth, and it depends on the fundamental constant of gravity. So it depends on 4 things. So if I step on the scales and I don't like what I see, I've got 3 other things I can blame. Maybe the fundamental constant of gravity changed overnight, the Earth's mass increased, or the Earth's size decreased. Works for me every time, all right? You can use that if you wish. Okay, so we measure the weight. We're measuring the force of attraction. We know from Newtonian gravity that the more stuff you have, the more mass you have, the more matter you have, the greater the weight will be. So therefore, when you weigh something, there's an indirect way. You're kind of roundabout measuring your mass. That works well here on the Earth. So in astronomy, all you have to do is measure the gravitational attraction of a star. So you ask the star to step on some scales, right? And weigh them up, right? Okay, that's not going to work very well. They're probably going to break the scales. So what we can do is we can look at the interaction that takes place, and what we look at is orbital motion. For instance, every month the moon goes around the Earth, and it's done that by the Earth's gravity. And by taking the orbital size and the orbital period, we can apply the generalized form of Kepler's third law, which you can derive from Newton's law of gravity, and voila, you can find the Earth's mass. We do the same thing with the other planets. Jupiter has a bunch of moons or satellites, natural satellites or moons orbiting it. Mars has a couple and so forth. We can measure their masses by the orbital motions of their satellites. And then we can find the mass of the sun by the planets that orbit around it. And we find out the mass of Jupiter is about 318 times that of the Earth. We find the sun is about 330,000 times greater than the mass of the Earth, and so it goes. And then when we get to stars, we can look what are called binary stars. You have 2 stars orbiting each other, going around under their mutual gravity. And by measuring how far apart they are and how long it takes to orbit, we can measure the masses of the stars involved. That's really cool, isn't it? And as it turns out, God arranged it so that probably most stars are members of binary star systems. Now, why do you suppose he did that? Well, maybe he did that so astronomers like me would have something to do to find the masses of stars. Now, why is that important? Well, because we have a wonderful theory about how stars work, and that theory makes several predictions. And one of them is, if you tell me the mass of a star, I can tell you things like how large it is, how bright it is, what its temperature is, and so forth. And all this information we gather by looking at individual stars allows us to build up a big collection of data that we can then use to compare to our theories, our models, and there's good concordance there. So it's a good check on physical reality. So I'm very thankful that God saw fit to make a bunch of binary star systems. I'm not being flippant. I think he really did that for a purpose. Sometimes astronomers ask the question, why are there so many binary stars? Because God wanted to make them for us. Creation, in many respects, is all about us, folks. And that's just a small part of it. Now, as it turns out, for more than 4 decades, I have been studying a particular type of binary stars called eclipsing binary stars. And what you have with an eclipsing binary star are 2 stars that are orbiting each other. Typically, they're really close together, and the system is really far apart, so you don't see the individual stars. If you look at it through a telescope even, the light's going to blend into a single point of light. Imagine looking at headlights of a car 10 miles away. It's going to be one spot of light. However, if we happen to look at the orbit nearly edge on, then once each orbit, one star will pass in front of the other, and that star will seem to dim. And then half a period later, the other star will pass in front, and the star will dim once again. And by studying how the light dims and recovers, we can figure out a lot of things about these stars. And I got a little short video clip that will illustrate this. I've got 2 stars here. One's a larger star, and it's blue, which means it's hotter. And then I have a smaller red star, it means it's cooler, and they're orbiting around each other. And you'll notice right there the red one goes behind, and now the blue one goes behind. The red one goes behind, the blue one goes behind. Now, running across the bottom is a little timeline. Time increases from left to right across the bottom. This little green dot goes across, and this light intensity is vertical like this. So it comes across and it dips, and then it repeats, dips, and it dips. We call this the primary eclipse because it's deeper, and this is called the secondary eclipse because it's shallower. Now notice that the hotter star is eclipsed at the primary eclipse right there, and the cooler star is eclipsed at the shallower secondary eclipse. That's pretty basic physics, and I don't want to take the time to tell you why, but it is, if you understand the Stefan-Boltzmann law, yeah, y'all just brushed up on that last night, didn't you? You understand exactly what's going on. All right, so that's a pretty simple system. The stars are far enough apart that they're shaped like spheres. It's pretty simple, and we can look at the depths and the shapes of those eclipses and figure out lots of things about the stars, including we can infer the masses out of it. Now, when stars are close together like that, though, they raise tides in each other. The stars that I typically look at, the periods, orbital periods, are anywhere from about 6 hours to about 20 hours. How long does it take the Earth to orbit the Sun? 1 year. So how far apart do you think the stars are if it takes like 8 hours to orbit each other? They got to be really, really close. And when you do that, the stars can raise tides on each other so that one star might be kind of football shaped, or even both of them may be kind of football shaped. Depends on what's going on. And I can illustrate that by altered here, a new little thing. There you go. This is a close system. And what's going on here, the red star, the cooler star, is a little bigger than it was before. And notice that the more massive star, the hotter blue star, has raised quite a bit of tide on that red star, the cooler star, and it's kind of made it like an extended egg. You know how an egg has like one little lobe that sticks out like this? And it's got points towards its companion star. And the tides are being raised to do that. And if the tide is high enough, you can actually pull matter from that red star onto the blue star. Let me interrupt myself here for a minute though. Notice because of the odd shape that the stars have now, it's changed the light curve. Before it was flat outside of eclipse, now it's actually over here in a secondary eclipse. It kind of starts going down and then goes up more gradually than before, and you get variations all throughout the light curve. I can take a look at a light curve which we observe. My research partner and I have been working together for almost 25 years on this. And we do these systems all the time. And when I just take a look at the light curve, and I can tell you immediately what we're dealing with many times, just because I've done so many of these. You can tell a lot just by looking at it. Now we apply a model to this and get more precise information, but you can see all sorts of clever things, this and much, much more. Let's get back to the matter though. If the tides are high enough, then the blue star there could pull matter from its companion through that little point that's pointing toward it, and the matter would then fall towards the blue star. We call this mass transfer. And over the years, I've seen abundant evidence in a lot of my observations of this mass transfer going on. It's a very real effect. And we've invoked it to explain a number of things, but we're not just pulling it out of the air. We actually observe these things going on. Now, there's also a thing called angular momentum. If you've studied physics at all, you'll know about that. And what happens is that matter transferring from the one star to the other has angular momentum, and it doesn't go straight down onto the other star. It tends to shift to one side, sort of like the Coriolis effect on the Earth, causing air motions to bend to one side. And when it'll swing around and come back, and it'll smack into more material coming in, and it will form what we call an accretion disk around the recipient star. Can you see on the blue star there, there's kind of like a halo around its waist there? That's the accretion disk. So material from the donor star doesn't fall directly onto the recipient star. It falls into that accretion disk. It's gas. It makes this disk all the way around, and you get this viscous motion, and it kind of robs it of orbital motion. It heats it up, and as it does, the gas spirals down onto the secondary star. Yes?
Are these stars spinning on an axis?
Yes, there's a orbital axis and there's a rotation axis for either star, and they're typically parallel to one another. Okay. There's no tilt to speak of. When they're this close, the transfers of mass tend to balance those up so they're all parallel. That's a great question. I've never had anybody ask me that, but that's exactly what's going on. Great question. All right. So this mass transfer happens, and it does some very interesting things. I could spend a whole talk just on some of the accretion disk phenomenon and what they do, but again, that's not my point.
Just a quick question. I only asked that because that red star, if that's spinning on an axis,
yeah.
How is that holding that axis straight up and down like that at that shape?
Oh, well, the axis is passing through the center of mass, and it's going to be off-centered a bit from what you're seeing here from the side. But it's not a problem.
But it's still spinning?
Yeah, it's spinning. Okay, I see what you're saying. What happened is these are tidally locked so that both stars are spinning and revolving at the same rate. So it's almost like a dumbbell going around like that.
So the mass is different. They're spinning at the same...
They're spinning on their axes at the same rate that they're revolving around one another. And that comes through a tidal interaction that takes place. That happens with other orbiting bodies, like for instance, the Earth's moon keeps one face towards the Earth all the time. It's been tidally locked by the Earth is the explanation. And that's a common phenomenon among the natural satellites in the solar system. Almost all of them do that. And if the planets were closer to the sun would do that. You heard about a lot of these exoplanets that are supposedly Earth-like, really close to what are called red dwarf stars. They're so close to their parent stars that it's expected that they have synchronous rotation, one side facing all the time. It's a very common phenomenon as well, and it's caused by tidal interactions.
Sorry for the interruption.
No, that's fine. It's great. You've noticed something that most people don't notice, and that's good. So no problem. All right, so that's again, I want to get across mass transfer, accretion disks, abundant evidence that both of those exist. I've seen it. I've been doing this for 40 years, and I see it again and again and again. Okay, tuck that away for future reference. I'm ready to talk about black holes. What is a black hole? Well, it's a very small but very massive object for which the escape velocity is greater than the speed of light. Now, if you take an object, a rock, a baseball or something, and you throw it up in the air, it will come back down. If you throw it harder, it will go higher, be in the air longer, but it will still come back down. If you fire it even faster, maybe fire a bullet upward, it will go pretty high, but it will turn around and come back down. It'll be in the air a long time. You put a rocket and you shove it up in the air like that pretty high, a few hundred miles, it will go up and it'll fall back down. What if you thrust a rocket fast enough it would overcome Earth's gravity and never come back again. The speed you have to launch that with is called the escape velocity, from the surface to infinity. And Buzz Lightyear said that first, I think. Anyway, the speed near the Earth for escape velocity is 25,000 miles per hour. It's about 7 miles per second. Orbital speed's a little less than that, about 5 miles per second, a little over 17,000 miles per hour. So you got to boost the square root of 2 faster than that to get escape from the Earth entirely. When the Apollo astronauts went to the moon 50 years ago, they had to blast off from Earth orbit, get up from 17.2 up to about 25,000 miles per hour to get to the moon. As it did, it slowed down the whole way. It was kind of puttering along towards the end, only about 1,000 or 2 miles per hour when it got to the moon. All right, escape velocity. Now, every object has an escape velocity. The sun has escape velocity and so forth. But how does the Earth's escape velocity of 7 miles per second compare to the speed of light? Well, it's 186,282 miles per second, so obviously it's a long way from being a black hole, isn't it? We can calculate how big the Earth would have to be, how small it would have to be a black hole. You'd take the Earth with all of its mass, about 8,000 miles in diameter, and if you squeezed it down to something a little less than 2 inches across, it would be a black hole. Yeah, it's pretty dense, isn't it? The sun, instead of being almost 1 million miles across, would be a few miles across. So obviously the things we're familiar with are not black holes. Now, these things were first hypothesized, believe it or not, way back in 1783, a man named John Mitchell, and he is probably the most significant astronomer you've never heard of, because he did a lot of cool things, but he just never got the attention a lot of other people got. His idea just was musing about this, and a few years later, the famous mathematician French Pierre-Simon Laplace wrote about it as well. And then it kind of sat there for more than 150 years. After all, if these things existed, big deal, you're not going to see them, was the thinking. And beyond that, they were so beyond anything, far, far beyond anything we had ever seen, they probably don't exist. It was like a nice hypothetical idea. But it's funny about those things. Hypothetical ideas have a way of being reality at some point. Mathematics is a great example. There are all sorts of mathematical things that people make up, and it has no real purpose until later. For instance, a guy named Boole came up with a little game that he made up on his own called Boolean algebra. He just kind of amused himself. Anybody ever heard of Boolean algebra? Where is it used? Yeah, it's the basis of digital computers. All the little things, the little zeros and ones you add together, that's all Boolean algebra. In fact, if you do any electronics like that, it's Boolean algebra you have to program in. I took a course years ago on that where I had little chips. I had to tell an LED to do stuff. It was really kind of cool on these things. All right, the modern theory and the name came along in the 1960s. By the 1960s, people began to realize these things might exist. They were starting to discover things in space that defied explanation any other way, but could be explained by black holes, as it turns out. So there was a theoretical physicist back then, back around 1963, who started calling these things black holes in comparison to the black hole of Calcutta. You've probably heard from history. Nobody who went into that thing almost came out alive, just like black holes. Once you go in, you're not coming back out. Now, I will not tell you all the physics involved, but here's an artist's conception of what a black hole may be like. The black hole is down here at the center of this thing. Now, it's not that black circle you see there. That black circle is way too big. The black hole is a little tiny dot down at the middle. And let's suppose that matter is infalling to this thing. Right now we won't worry about how the matter is infalling, but there are a couple of different ways you can do that, and I'll give you one in a moment how it can. But matter is falling into this thing, and by angular momentum conservation, it doesn't fall straight in. It's got some little orbital motion, so it ends up swirling around like this. You end up with this accretion disk you can see there that forms. And you get these viscous losses. Whenever you have any kind of fluid, a gas, a liquid coming along, it rubs against each other. You get wind resistance, collisions that take place, and this turns into heat. We say it thermalizes the orbital motion, turns it into random motion, which you know from grade school science, when you heat something up, you make the particles move faster. What's going on here? So it gets hotter, but as you rob that orbital energy, it causes it to fall inward like this. And as it does, it spirals in. So it's sort of, you've seen these pictures in movies and such, spiraling around like this, like a draining like that. This is exactly what it's doing. It's spiraling down, picking up speed, going inside of this thing. As it does, it gets hotter and hotter. So the coolest part out here is there, and as you go towards the center, it gets hotter and hotter. And down towards the boundary of the black hole, which we call the event horizon, just a little bit out of it, the temperature can be millions of degrees. It can be very hot. And this gives off X-rays. And X-rays produced in large quantities, very difficult to do. So when we see those X-rays, it gets our attention. Now, you see this jet-like thing spiraling up here and the other one down here. The black hole in the middle can have a magnetic field. In fact, it's almost always going to have a very powerful magnetic field. How powerful? Well, if you had braces, it would yank your head off. Okay, that's how powerful these things are, if you have steel in them, of course. And when it's hot like that, you have ionized gases, electrons in the nuclei of atoms, and they're charged particles moving at a very high speed. And when you have magnetic fields with moving charges around them, you accelerate those charges. And you can end up with a complex interaction, a jet of energy, radiation, and particles going this way and going that way, perpendicular to the disk. These are called jets. Now, what's going on is it's like an engine working here. Material is falling into the black hole, and as it falls, some of that energy that it has is being transferred to other particles that are being accelerated. It's kind of a trade-off. Things fall in, things get blasted out, both happening at the same time. So it's not all just falling in. I want to make a point here that this stuff is not being ejected from the black hole. It's being ejected from a region above, near the black hole, but not in the black hole. As stuff falls in, it transfers energy to stuff going out. Make sense? So you have infalling and you have outgoing jets. That's the understanding. It's been around since the 1960s and honed up since then. Now, this is an artist's conception, but this little inset is a radio telescope image of this object called GB 1508 plus 5714. That's basically a catalog number that identifies where in the sky this object is. And they think this white blob here is the disk, or something around the disk, and this is one of the jets. Sometimes one jet shows up, sometimes both jets show up. But we have identified a number of objects with radio telescopes and with X-rays that we think are these things. Now, we class black holes according to their masses. There are what are called micro black holes. These are very small, maybe planetary size, maybe asteroid size. And these are hypothetical. Nobody knows how they could form. We've never seen one yet, but there's no reason why they can't exist. We just don't know if they indeed exist. Stellar-sized black holes, these typically have about 3 to 20 times the mass of the sun. And I put a check mark next to it because there's good evidence that these things exist. And then there are intermediate-sized black holes. These have thousands of times the mass of the sun. A number of years ago, I got to thinking, could you have something that's thousands of times the mass of the sun? So I started looking through the literature, and I found out I have all these great ideas, like inventions and such, and then when I start checking into it, I find out somebody's already thought about it. So that happened to me. I discovered intermediate black holes about 20 years after somebody else thought of it, and I'm a little late. But I had a good idea, at least, you know. I've had several inventions I've thought of, only to find out somebody's already made it. So you got to be a little fast on these things, and I'm unfortunately not as fast as some other people. Then there are supermassive black holes. These would be millions of times the mass of the sun. I put a check mark next to them because there's good evidence now that they exist as well. So I'm going to spend some time talking about those. Remember I talked about the accretion disk. If you have a black hole sitting here with an accretion disk around it, where is this mass coming from? Well, there are a couple of ways you can do that, and here's one of them. Suppose you have a binary star system. Well, kind of like the ones I observe, except on steroids, because these are really exotic ones. I do mundane things, but the same sort of physics involved. Suppose that one of the stars is a black hole, right there, and its strong gravity, it's close to its star it's orbiting around or co-orbiting with, and its strong tidal interaction can lift material off, and as it does, it zips down to an accretion disk. There's a spot where it's being fed into it. There's a bright spot there, and the red to yellow to white coloration indicates an increasing temperature. If anything else, the stuff is being squeezed into a smaller volume because it gets smaller down there. And because of that machine or that engine I was talking about, transferring energy of things falling in to things jetting out, you can get 2 jets or 1 jet coming up from. Again, an artist's conception of what it would be like. So what I'm suggesting is that we can detect these things in close binary stars, really close binary stars, where one of the companions fills what's called its Roche lobe. You know that kind of egg shape or football shape? That's the Roche lobe sort of shape. A guy named Roche worked the mathematics of this out a couple hundred years ago. And if it fills its Roche lobe, that's where you get mass transfer. You can go from one star to the other pretty readily. And it settles into that accretion disk. Now, if you studied physics, we can talk about the steep gravitational potential well. If you don't know what some of these terms mean, don't worry about it. It's not that important. All that means is that as the material falls down, it gives up energy. A good example I can give here is a hydroelectric dam. You all seen those before? You don't have any here locally. Up in Wisconsin, they have some. In Piedmont and South Carolina, where I used to live, they had some. You need a steep gradient for these things to work. And so you build a big dam here and you impound water behind it, and then you'll have a pipe that allows the water to drop down and come down here, and it picks up speed as it does that. What it's doing is it's converting gravitational potential energy from up here, when it's sitting still, it picks up speed and converts it into kinetic energy, energy of motion. That fast-moving water then hits a turbine, hits those blades. On the turbine, it spins around, it slows the water down, it transfers its motion, its energy into the spinning turbine, which then is connected to a generator, and it produces electricity. All you're doing is you're taking gravitational energy, turning it into kinetic energy, converting it into electrical energy. All you're doing there. Well, the stars are doing the same thing. As this stuff transfers down, it's going through a very steep potential gradient. Imagine a dam about 1 billion miles high. Then you get an idea of how much energy there is involved here. It's a very high dam is basically what you have here. And as this does this, it thermalizes the motion. That is, it turns it from orbital motion into heat. It's random motion now. So you heat this up, and it gets so hot it gets to be millions of degrees, and that gives off the X-rays that we can see. Now, there's a problem here. We can't see X-rays from these sources from the ground. Why is that? Because the atmosphere blocks it out. Too bad for astronomy. But what's bad for astronomy is good for everybody else. Why is that? Absent the protective layer of the Earth's atmosphere, those X-rays would sterilize the planet. So it's good we don't have those X-rays coming through. Good for life, bad for astronomy. So what we've done, starting back in the 60s, we would take a rocket and launch it way up into space, and for a few moments it would observe some things, and it would come back down again. And then by the 1970s, we started sending up orbital things. Now we have like 3 or 4 X-ray satellites that are orbiting around the Earth. We've launched, the European Space Agency's launched various instruments aboard, and we've just been doing this regularly for decades, observing these things. And when they first started discovering these X-ray sources back in the 1960s, they didn't know quite what to make of them, but then they hit upon the idea of black holes, and that's what revived the black hole discussion after more than almost 200 years at that point. Again, another artist's conception, mass being pulled off of one star, falling into the black hole down there. So this produces what are called X-ray binaries. We call them XRBs for short in the literature. Now remember, part of the name there is binary. What's so important about binary stars, did I say? It allows you to find masses of stars, doesn't it? That was the big deal, like God is so good to us about that. So they're binary stars. We can solve for the mass. Now here's the rub. Because only one star is visible, the X-ray, the black hole's not visible, we can't get the individual masses. We get the two masses together. Now imagine that you and a friend step on a set of scales together. When you do that, what do you have? You had your combined weight, your combined mass, don't you? But if you know your mass, how can you find your friend's mass? You take the difference. Just subtract your weight off, and whatever's left has to be your friend, right? That's an easy way to do that, isn't it? So, what we can do many times is because of our knowledge of, remember how if we know the mass of a star, we can figure out its other properties. So if we look at the properties of the star we can see, we can infer what its mass is. And so if we subtract it from the total, what remains must be the mass of the object we're not looking at. So it's the difference of these things. The difference of the two will give you the compact object's mass. Now I've switched the language here. I'm not calling it a black hole anymore. I'm calling it a compact object. Why am I doing that? Well, there's one other little wrinkle coming along here. There are two types of objects that are capable of producing very, very strong X-ray sources, X-ray binaries. One you've already mentioned, I mentioned here is a black hole. The other one are neutron stars, which I've not mentioned. Neutron stars were predicted back in the 1930s. This is a very compact object, about the size of a city, a few miles across, very massive, and it's made of nothing but neutrons packed together to nuclear density. You do know that normal matter is mostly empty, correct? You know that? If you wanted to make a model of an atom, you could take the nucleus, it could be a baseball, and the electrons would be BBs, and they might orbit several miles from the nucleus. And so here in Lake County, you would have one baseball with its electrons going around. Down in Cook County, you've got another baseball with electrons going around. And over in DuPage County and Will County, you get how many counties are there in Illinois? Nobody knows? How many other? 120? That's a lot. Kentucky has that many. Okay, you got maybe about 100 counties, right? So you got about 100 baseballs, right? Now, there's a lot of empty space between those baseballs, aren't there? Now, what would happen, instead of doing one per county, suppose you started stacking up baseballs, just dumping them down on the ground to a height of several miles. How many baseballs could you put in Illinois? I have no idea, but it's going to be a bunch, isn't it? That's what's going on with a neutron star. All those neutrons are actually touching each other, so the densities are incredible. In fact, the density, this mass and so forth, is very close to that of a black hole, as it turns out. So they're capable of producing these X-rays as well. So when you see an X-ray binary, you know you're dealing with a compact object. It could either be a neutron star or it could be a black hole. How do you know which one it is? Well, as it turns out, there's an upper limit to the mass on a neutron star. That's very well established. I don't have time to talk about it tonight. But the most mass that a neutron star can have is about 3 times that of the sun. So if you find a compact object in an X-ray binary system that has more than 3 solar masses, can it be a neutron star? No, it must be a black hole. So let's look at a couple of examples. The first X-ray, one of the first X-ray sources discovered back in the early 1960s is called Cygnus X1. It's called that because it was the first X-ray source discovered in the constellation Cygnus. That's why we name it. It's a binary star. And as we've studied it over the years, we figured out that the mass of the compact object is 11 times the mass of the sun. Can it be a neutron star? No. Ditto for V616 Monocerotis. It too has a mass of 11 times the mass of the sun. And there are several score, maybe now a couple of hundred X-ray binaries with a compact object. Sometimes it's less than 3, but many times they're more than 3. I've seen 15, I've seen 10, really over the chart beyond what a neutron star can be. So consequently, there's very good reason to believe that black holes, stellar-sized black holes, are real. We have numerous examples, probably a few hundred now. All right, I haven't kept up in the numbers. All right. Now, what about supermassive black holes? They developed an idea probably 40 years ago that there were some funny things going on inside the nuclei or the cores of certain galaxies, including our own. What's going on there, you get orbital motion very quickly going around, and we can do the same sort of physics we did before with orbital motion and figure out how much mass there has to be to explain that. And over the years, we've developed the ability to probe this better and better. It's difficult to see into the cores of galaxies because of the obscuration by dust that's there, but we've been able to do it with certain wavelengths. And the HST, the Hubble Space Telescope, has helped tremendously. So we detect it by motion of stars or other objects around the center, and you can determine the mass like we did before. And when you do that, you find millions of times the mass of the sun. And in fact, this mechanism has been invoked to explain a number of exotic objects. We have what are called AGNs, that's the abbreviation for active galactic nuclei. Most galaxies seem relatively normal, but there are some galaxies, the cores of which are doing really weird things, pumping out a huge amount of energy, and they've known about this for like 70 years. And the only way we can explain that is if you have a supermassive black hole there. Then there are quasars, QSOs, or quasi-stellar objects. Those were discovered in 1963. Pardon?
I'm asking myself what is going on AGNs. They're like massive energy sources.
Right, it's a galaxy, but at the core there's a very tiny little region that's pouring out unbelievable amount of energy.
Yeah.
And quasars are pouring out an unbelievable amount of energy. One of the first quasars discovered, 3C273, it's about 100 times brighter than the Milky Way galaxy, which we're in. The Milky Way galaxy has a few 100 billion stars. So imagine taking a few 100 billion times the brightness of the sun and then increasing that by a factor of 100. Now you're talking about a few trillion, all right, a few tens of trillions. Well, I haven't told you the best part yet. You're pouring out the light of 100 times the brightness of a large galaxy, and you're doing it in a volume of space about the size of the solar system. Yeah. It'd be like having the most unbelievably powerful engine you've ever imagined, and when you open up and look at the engine, it's about this big. You know, just, you know, you could...
I haven't even gotten to my question.
Yeah, okay. I'll give you some examples. Here is M87. It's an elliptical galaxy 30, 40, 50 million light years away. Down on the core, you got a bright knot with a galaxy surrounding it, and then you got this big jet coming out of it. Just one. We can't see the other one apparently, if there is one. But radio telescopes have measured blobs in that jet, and they see the motion changing from year to year, the position changing, and that stuff is moving at like half the speed of light. It's incredible. There's something deep in there that's blowing this stuff out. And we think there's a supermassive black hole. Now, you may have seen this picture about a year ago. This was touted as being the first picture of a black hole. You all hear about that picture? It's called M87 star. This is the critter at the center of the M87. However, I object. I wrote an article about this. If you hear about a news item and you want to hear our perspective from Answers in Genesis, go to our website. We have tens of thousands of articles there, fully searchable. Anybody go to the website very often? AnswersInGenesis.org. When this came out about a year ago, I wrote an article about it because I thought it was important. We had questions about it. And it's not really a picture of the black hole. What you have here, this is done by radio emissions, so it's not a light photograph. This ring you're seeing here is kind of a smoke ring. That is the accretion disk. This is the first time we actually have an image, clear image of an accretion disk. We've never had that before. We've detected it by various means, but we've never actually made an image of the thing. We can get radiation from it, but getting an image, it's a different story. And the black hole is somewhere inside of this little opening there. That's not the black hole. The black hole is much smaller than that. But that's the accretion disk measured in the radio part of the spectrum. Other examples, at the center of the Milky Way, there's an object called Sagittarius A star, and it's got a complex of things. There's an object in there called S2, and it orbits in a very eccentric orbit at a period of 15.2 years. At its closest approach to the center of its motion, once every 15 years, it's only 17 light hours away. That's about the size of the solar system, outer regions of the solar systems. And when you do the orbital calculation to determine how much mass there must be there, it turns out to be 2.6 million times the mass of the sun. And what do you see inside of that orbital motion? Nothing. So it's got 2.5 million times the mass of the sun in a very tight orbit the size of a solar system, but no energy coming off that you can see. It's got to be a supermassive black hole with a radius no more than 17 light hours, again the size of the solar system. M104, it's a nearby galaxy 30, 40, 50 million light years away. Stars near its center tells us that the black hole there is 1 billion times the mass of the sun. And recently discovered, the record holder so far, it's about 6 billion times. It's another galaxy about 6 billion times the mass of the sun. Incredibly big things. A picture, radio image of the Sagittarius A star. Here's a photographic light image of M104. Now, I've been talking about this for half an hour or more. Question, where's the evolution? I said nothing about where these came from. Said nothing about how they were made, how long they've been around. All I'm doing here is good operational, observational science of the here and now. What do we see and what does it mean? This is good science, folks, the kind of science we creationists love. Now what happens is people come along and they start saying, well, how did these things form? Well, at this point, I don't care. You can speculate all you want, but there's no evolution necessary to see the case for this. Now, there's no clear explanation for micro black holes yet. No one's come up with one. They may not exist anyway. Stellar black holes, they believe, come from implosions of cores of very massive stars that produce these titanic supernova eruptions. That's not quite been proved yet, but that's the thinking people have. There's no origin for intermediate-sized black holes. Mergers might account for that. You take smaller ones and add them together and finally end up with that. By the way, the LIGO experiment in the last couple of years has actually measured its gravitational waves. It's actually measured mergers of a couple of black holes. They're orbiting around like this, and they get closer and closer, and all of a sudden, they merge together. When that happens, it really ripples space, and they've picked that up. We've actually detected this now. And we can figure out a lot about the process that happened. So that might be a little evolutionary, except we actually witnessed it and it didn't take very long, as it turned out. It's pretty fast when it happens. Okay, what about the origin of supermassive black holes at the cores of many galaxies? Well, mergers perhaps, some sort of primordial process, nobody has a clue. As it turns out in retrospect, it's not so shocking that large galaxies have this. There ought to be something at the center anchoring those. And so in my estimation, I think God probably made these on day 4 when he made galaxies. You need something. It's like a foundation of a building. Can you build a building without a foundation? Not a very good one, can you? You need a foundation there, and these things actually are the anchors of the foundation around which the whole galaxy depends. So I see evidence of design here that I don't have to think of an evolutionist scenario. I think this is good science, and I think we creationists should be embracing this. We shouldn't be fighting it. Okay, what about dark matter? Well, it was first suggested by Fritz Zwicky. I just love to say that name. Don't you love that? A Swiss-born American astronomer in 1933, he looked at the Coma cluster. I've already alluded to galaxies. Galaxies contain billions of stars, and they clump together in groups we call clusters. You'll see just hundreds of, maybe 1,000 galaxies that appear to be connected, physically connected, and they're moving in our line of sight like this. So what Zwicky did is he measured their motions. Assuming their orbital motions, he was able to figure out what the dynamic mass was. Remember what we've been doing all along? We look at orbital motion. That tells you how much mass is there required to explain that orbital motion. He did this for the Coma galaxy cluster, and when he did, he got the dynamic mass. Then he could compare it to what we call the lighted mass. As it turns out, if a galaxy has more mass, it'll have more stars. And the more stars you have, the brighter it will appear. So there's a nice relationship between the mass that you have and the amount of light you get. So if you look at the light, you can figure it out. As it turns out, about 1 mass of the sun produces about 1 light of the sun. That's because the sun's kind of a mid-range average star. Works out pretty well. So, okay, Fritz Zwicky measured how bright all the galaxies were in the cluster, and he added them all up and divided by this and got the lighted mass. And when he did, he compared it to the dynamic mass, and the dynamic mass was about 10 times brighter, greater than the lighted mass. He went to another cluster, and he got the same sort of result. In fact, every cluster he looked at, you got a range of about 5 to 20 times, with an average of about 10, more dynamic mass than lighted mass. He called this, spoke German, he called it Dunkelmatter, which means dark matter. Other people called it missing mass. They called it that for decades. And for more than 40 years, astronomers ignored this because they didn't know what to do with it. Now, here's a picture of the Coma cluster. Okay, most of the objects you see there are actually galaxies. This is a star, a foreground star in our own galaxy, as is this one. Anything that's extended, kind of fuzzy, those are all galaxies. And there are thousands and thousands of clusters of galaxies, each one consisting of thousands of galaxies many times. Okay, here is the Andromeda galaxy. Now, a guy named Babcock, back in 1939, 6 years after Zwicky did his first study on clusters of galaxies, did something very clever. This galaxy is similar to our own Milky Way. It's round and flat, and it's got a bulge in the middle, so it's kind of like an over-easy egg. And we're seeing this nearly edge on, about 13 degrees out of edge on, because it's not a big circle, it's a big flattened ellipse, isn't it? Everybody understand? Now, things are orbiting around under mutual gravity, which means if you look on this side, the stuff is moving towards you, and on the other side, it's moving away from you. Do you all understand that? Now, stuff in the middle is not moving that fast. This is moving towards you, not so fast. This is moving away from you, not so fast. But as you go away from the center, it increases in speed. Now notice, where do you see most of the light coming from? It's coming from the center, isn't it? And as you get out of the core of the galaxy, this is the core, when you get out of the core, the brightness starts to drop pretty rapidly out towards the edge like this. See what I'm talking about right there? So that would suggest that you got a concentration of mass at the middle, and the mass decreases pretty steadily out to the edge to nothing. Now, what you can do is you can use the velocity you measure all along the axis here as a probe for how much mass is inside the galaxy. And for what you see on the lighted part, the speed of rotation or orbital motion ought to increase out to about here, and then beyond that it ought to steadily decrease all the way out to the edge. But when Babcock did this in 1939, he found out that the speed actually stayed high and even increased as you went farther and farther and farther out. Now, if you're going to apply Newtonian gravity and physics to this, you come up with a startling conclusion. Most of the mass is out here. There's an anti-correlation between the lighted mass and the dynamic mass. How much so? When he got out to the edge, he totaled it up, and he found out there's about 10 times more dynamic mass than there was lighted mass. Same factor of 10 with a very different result, except now instead of a cluster of galaxies, it's an individual galaxy. And on top of that, it told you where all this unseen matter was. It was not here in the middle where all the light is. It's out here near the edges, what we call the halo of the galaxy. There's an anti-correlation, in fact, between light and mass. That is weird. Again, people ignored it. Well, in the 1970s, Vera Rubin and Kent Ford went on a decade-long collaboration. They used some of the largest telescopes in the world. Technology had advanced to the point. Babcock was barely able to do this with the Andromeda Galaxy. By 1970, technology got to the point these two pair were able to reduplicate in a better way what he did for Andromeda. And then they started looking at other galaxies. They had dozens and dozens of galaxies, and they got the same strange result every time. So now you have two lines of evidence telling you very strongly that you have dark matter, and it's telling you where it is. And I'll just go to the plot. The plot here has velocity going vertically, and then distance is from the center of the galaxy. And the expectation is as you move out from the center, the speed of orbital motion ought to increase very rapidly. And then when it gets outside of the core, it ought to start dropping down like this. but instead it remains high and even goes to high values. And again, the only solution we can have is out here there's lots of mass, more mass than you have where all the light's taking place. Very strange result. And again, astronomers ignored this for 30 or 40 years. By 1980s, astronomers finally threw in the towel and accepted this because of Rubin and Ford's work on this. Keep in mind the astronomers had to be dragged screaming the entire way to do this. And there's a third line of evidence that came along since the 1980s, more the 1990s, gravitational lensing. You can look at a cluster of galaxies relatively nearby, or maybe 1 billion light years away, looking at a more distant object, and the light gets lensed, and as it does, you can use that as a probe of where the matter is in the cluster. Here's an example of that. Here is a cluster called Abell 1689. All these little smudges of light, those are all galaxies within a cluster, but if you look very carefully, there are these little streaks like this. Over here's one, there's another one. They look almost like a bullseye pattern. Get down here so I can see it better. There's kind of like a bullseye pattern. Here's one, there's one, there's one, there's one. They're all kind of oriented, and there's a couple up here. Okay, they're kind of oriented in a bullseye pattern. Those are actually gravitational lenses. The gravity of the light, the gravity of the cluster is actually bending the light of a much more distant object and forming those little images. And by looking at those images form, you can get a probe of how much mass is inside of this. And guess how much mass they find? About 10 times more than they can account for by the light given off. Third line of evidence in all of this. By the way, where's the evolution in this? There isn't any, folks. This is good observational science. Now, what is dark matter? Well, we don't know. There have been many theories. However, we've eliminated just about every one of those theories by doing additional studies. A lot of my creation brethren misunderstand this. Another paper comes out. In fact, I just saw that last week. Another paper came out. One of my creationist buddies sent out an alert to a bunch of us and said, oh, disproves dark matter once again. I said, not so fast. It didn't disprove dark matter. What it did is it disproved one of the possible explanations or identifications of dark matter. Dark matter is still there. We just don't know what it is. It is, whoever discovers the identity of dark matter is going to get a Nobel Prize in physics. I'm real good at identifying the questions. I'm not very good at answering them, but I know the good questions when I see them. Guaranteed you will get a Nobel Prize if you answer this problem. I suspect it's probably a form of matter we don't even know about yet. And that's interesting because they have a theory of particles, what's called the standard model of particles. You heard of the Higgs boson? Who's heard of the Higgs boson there? And so that was the last particle to go into all of this. And when they did that, they don't have any room for anything else, which means that if you identify what it is, it's going to have to change the standard model of particles. By the way, did you hear about the Higgs boson that went into a Roman Catholic cathedral? No. A priest came running over, immediately saw him and said, you can't come in here. You call yourself the God particle. You can't come in here. You'll have to leave. That's just sacrilegious. We can't have that. And the Higgs boson said to him, the priest, he said, hey, without me, you can't have Mass. So, actually, you got a bunch of astute people here. I think they got the joke. That's a pretty high-powered physics joke, right? I got a few more, but I'll save them for later. All right. So again, where's the evolution? There isn't really any here. However, once the astronomers by 1980 began to accept dark matter, it took the cosmologists another 10 or 12 years, and they got in on the game. They said, "Oh, really?" You see, cosmological models assume that gravity is a dominant force in the universe, and gravity depends upon matter, how much mass you have. If you leave out 90% of the mass, how good can your model be? Not very good at all. So they were as late as the astronomers were. The cosmologists were even slower in coming to this. Now, what happens though is it becomes another free parameter you can manipulate in the Big Bang model. And you can manipulate that to solve other little problems that people have. And that is where many of my creation brethren, the physics people particularly, come in to the conversation, and all they see is all the evolutionary discussion about this. And I'm saying, so it must be evolutionary ideas that dark matter doesn't exist. I'm saying, not so fast. You weren't around for decades before that when we were thrashing through this. There's a strong operational science case to be made here, and you're forgetting that entirely, or maybe you don't even know about it. But there's a strong case to be made for dark matter. We ought to embrace that and try to make it our own. I already argued that I think there's a design aspect of supermassive black holes, because how else can you have a galaxy without it? Finally, I want to talk about dark energy very briefly. Back almost 100 years ago, Edwin Hubble discovered what we call the Hubble relation. What he did is he measured the distances of galaxies, and he measured their redshifts. And what he found out was the farther away a galaxy is, the faster it's moving away from us, or its redshift is greatest. Redshift would generally indicate that galaxies are moving away from us. And so this is an idealized situation, but if you plotted real data on it, it would scatter around this line, and the slope of this line is what we call the Hubble constant or Hubble parameter. It's a measurement of how rapidly the universe is expanding. By the way, all Hubble found was a correlation between redshift and distance. The interpretation is that the universe is expanding, but keep in mind it's an interpretation. There could be some other mechanism at play, and the universe may not be expanding at all. I'm not suggesting it's the case, but my mind is open to that. Until I find another mechanism, I'll go with expansion. But it's an interpretation. Never lose sight of that. Now, remember I talked about gravity being important. If the universe, the Big Bang cosmology, if the universe is expanding, and it's been doing it for billions of years, then the gravity of the matter in the universe should be acting to slow that expansion down. Remember the analogy of throwing an object up in the air? Gravity will slow it down and maybe reverse it, maybe it won't, but even when you launch greater than escape velocity, it slows down as it does that. Well, I remember reading about this 50 years ago when I was in high school. They said this expansion, if there's gravity acting, and there is, what it ought to do at extremely large distances, it ought to cause this straight line to curve upward a little bit, like that. It ought to depart from linearity and ought to curve upward at great distance, because in the past the expansion would have been faster than it is today. The problem is, we couldn't get reliable distances out very far. We can only get out to about here maybe with reliable distances. That changed in the 1990s. They already knew that type 1a supernovae they're very powerful explosions, and they have a very narrow range in brightness. So when you see one, you know how far away it is. And they're not real common when they occur, maybe once or couple of times a century in a particular galaxy. Well, what they came up with in the 1990s, you have a medium-sized telescope. Every night it opens up. It's a robotic telescope, and it will go to hundreds of galaxies and take photo after photo after photo after photo. No astronomer even involved, nowhere near the place. And it will immediately compare the photos it took to a template of a photo it took earlier, lay them on top of each other, subtract them off, and if nothing is added to the new photo, then you'll get just a blank picture. But what happens if there's a supernova that takes place? When you subtract off the template, you've got a bright spot there. When that happens, the computer sends an email message to an astronomer someplace. He drops what he's doing. He goes to the big telescope he has. He zeroes in and studies this. It's a great thing they're doing. We've now discovered a few hundred supernovae, type 1a supernovae, in the last 25 years. Great technology we have today. Not impossible to do just 30 years ago. Now we can do it. In the 90s they could do it. So two different teams were looking at this project in the late 90s, mid to late 90s, and they were looking for this upturn that they expected at great distance, for the first time able to reveal that distance. And they were tearing their hair out. You know why? They found a downturn. They were looking for an upturn, and they found a downturn, and they didn't dare publish that because it made no sense. Until they found out about the other group. Then they started communicating, and that gave them boldness, and they published it. Now, if An upturn at great distance means the universe is slowing down its expansion. What do you think a downturn means? It means just the opposite. It means the universe is expanding faster, acceleration in expansion. Interesting. Now, this was something anticipated by Albert Einstein 100 years ago. He introduced what he called the cosmological constant. He did that for a reason. Later on, he retracted it and people kicked it to the curb, and that's where it's set for 70, 75 years. However, it came back in the late 90s. What's going on? Well, they decided to call it dark energy. I hate that name. It's kind of in parallel to dark matter, has nothing to do with it. They think there's some sort of field in the universe that is accelerating the expansion of the universe. It's similar to Einstein's cosmological constant, the difference being his was a constant term. This is maybe a time-varying term. We don't know yet. It's extremely model-dependent. It becomes another free parameter, and there are some evolutionary ideas behind it. But the point is, it's based upon some very good data. What does it mean in a biblical cosmology that is not a Big Bang cosmology? I don't know. Because you see, we don't have a model yet. I'm hoping that some young people coming down the pike now will be prepared to actually make a model for us. I don't think that's my calling, it's not my expertise, but again, I'm pretty good at identifying the questions, I'm just not too good at answering those questions. So I'm not quite as bullish about dark energy as I am about dark matter and black holes, but I do recognize the fact that there's some important data there, and we need to pay attention to that, and we need to claim it for ourselves, and we need to interpret it in terms of a cosmology which we don't have yet. But hey, I'm patient. I've been patiently trying to put together this creation model of astronomy for a very long time. All right. Well, I will mention just a few resources. I've got the Danny Faulkner table out there with my 5 books, and then I got a few books from some fella named Ken, what's his name again? Ham? Oh yeah, Ken Ham. All right, so we got a few of his books too. But anyway, I have Universe by Design, which is a book, my first book came out 15 years ago. It's on cosmology, Big Bang and other things. It's more technical than the other books. The portions of it are a little hard to read, but much of it is, I think, very readable. I will caution you, I've changed my mind about a few little things in it, but most of us still stand behind. I do need to revise that book. I've mentioned it to the publisher. We'll see what happens. The Created Cosmos, I wrote came out with 4 years ago. That is a study of the cosmology, or actually any astronomical references found in the Bible. Such books have been written in the past, but have been more than 100 years since any book had been written, so I thought it was time to revisit this. When I finished that book, the next year I decided another book needed to be written, The Created Cosmos. It is I'm assuming the Expansive Heaven. This is a book about the creation science of astronomy. I didn't go in that first book, so I needed a second book to talk about it. And I made up similar size and shape so they can kind of be companion books. I refer to the first book and the second book quite a bit. And since I picked a blue and a red cover, I call them respectively my Democratic and Republican books. So there you go. We've got a lot of election jokes, don't we? And I have two other books out there. I'll be happy to talk about those. But thank you, Ken. You want to close us out here?